Hello, thank you all for joining me today. I'm going to go ahead and share my screen. Once again, my name is Vanessa Yan, and I am a staff product manager at OctoML. Today, I will speak about some recent industry-wide challenges I observed in AI/ML deployment and demo a tech stack one could use to overcome these challenges. So without further ado, I will jump right in. One challenge we observe in industry recently is that many enterprises face difficulties scaling up their existing AI/ML workloads on cloud GPUs. Due to chip shortages and the higher need for GPU resources in cryptocurrency mining, cloud GPU resources are getting scarce. Enterprises need a way to scale up their AI/ML workloads reliably under these constraints. And one way to do so is to switch to CPUs. However, switching is actually more difficult than it sounds. The first reason why is that many AI/ML pipelines are built with an assumption of having access to the GPU. Having to refashion these pipelines with dependency and versioning management for CPUs can take weeks of effort. Second, it is hard to ascertain early whether switching to the CPU is actually a viable solution in terms of meeting the latency or throughput SLAs specific to one's business use case. A common failure mode is doing weeks of work trying to switch to CPUs only to find that the latency SLA of the application is no longer met and that one has to revert back to the old GPU flow. The next challenge we see is the need for enterprises to cut costs. Given inflationary pressure in the economy and widespread worries about a recession, enterprises across many industries are tasked with short-term mandates to improve cost efficiency all around, including in their AI/ML workloads. For ML applications in production, actually 90% of total compute costs comes from inference, according to AWS. This is why it is important to figure out how to reduce cost per inference. And finally, on a longer time scale, we observe enterprises wanting to deploy AI/ML to unlock new business value and new use cases ranging from life sciences and autonomous driving to art generation and video captioning. However, not every enterprise has the same resources as FAANG companies in building customized deployment tech stacks from scratch. In fact, many enterprises don't even know yet what a canonical deployment stack should look like. And as a result, more than 80% of AI/ML models never make it past R&D phase in a production, which means enterprises are leaving business value on the table. We want to help enterprises automate away the pain and the long time it takes to set up a deployment stack, handle versioning management, and manually optimize models to work on different hardware targets. And here's how we envision OctoML solution can help. First, we help folks achieve hardware independence by making it easy for you to switch hardware while still making sure you're meeting the latency, throughput, cost budget, and other requirements specific to your business. Second, for any combination of model and hardware, we help you reduce cost per inference. We generate an automated experiment across state-of-the-art acceleration technologies to find the one that works best for you and package that up into a container that's immediately deployable on the cloud. And finally, we help enterprises accelerate time to market for their AI/ML models by automating away the pain of setting up and maintaining a deployment stack. And now I'll go into each area of solutioning in more detail. First, I will show you a user journey of how to achieve hardware independence via OctoML. Once you log in to the OctoML platform, you'll be first asked to upload your model. You can add models in any of the common serialization formats, including Onyx, TensorFlow, and PyTorch's TorchScript format. Once you've uploaded the model, you'll be prompted to indicate which hardware your existing AI/ML workload is running on in production OctoML platform runs a hardware fleet that's connected to all three major clouds. So you'll be able to select hardware from any of those clouds. Next, you'll be prompted to indicate what technical constraints your application has. If you have a real-time processing use case with a strict latency limit, you should select minimize latency as your goal. Instead, if you have an offline batch processing use case, you should select maximize throughput. Third, a lot of AI ML services on the cloud actually require you to balance both throughput and latency. Or in other words, maximize throughput while staying under a certain latency threshold. Let's select this option for the purpose of our example. Now, OctoML will recommend to you a few new hardware options you should experiment with. You can also add any other hardware targets you want to explore. After the exploration is complete, you'll have access to Docker and Python wheel packages that are immediately deployable to the hardware targets you've selected. In other words, we handle all the dependency management for you and package the necessary requirements for deploying your model. All you need to do now is download the Docker artifact or Python wheel, depending which format you prefer. I will also show you an example of how to deploy the Docker tarball in an end-to-end demo later in this presentation. Apart from getting the value of hardware portability, you also get to visualize the magnitude of cost reduction, latency, and throughput improvement unlocked by the OctoML guided experiment. For example, let's focus on the orange and green dots here, which represent the V100 GPU and Graviton 3 CPU, respectively. You'll see here that by switching from V100s to Graviton 3s for this model, we reduce the cost per million inferences by half of the original amount, while still staying within the desired latency SLA for this business use case. In fact, we even reduced the latency thanks to OctoML's acceleration technologies. Now, you may ask, what if I don't want to change the hardware target I'm currently using? Is there still a way to reduce cloud costs? The answer is yes. Using OctoML's acceleration technologies, you can reduce the latency or maximize throughput of your model for any desired cloud hardware. Reducing latency means you spend less time running compute on the cloud, so you're spending fewer dollars. Maximizing throughput means you're running more inferences in each unit of time. So you're better utilizing the hardware resources on the cloud and have less need to spin up additional servers to process your desired load. And finally, I'll now show you how OctoML helps data scientists and DevOps engineers accelerate time to market for their models. I'll walk you through an end-to-end example of how to deploy a YOLO v5 model from Ultralytics GitHub repository via the OctoML command line interface. Specifically, I will show you how to set up your local environment, how to package and deploy the model locally, and finally, how to deploy on remote hardware while unlocking the hardware independence and cost reduction value props. All right, I'm going to pull up another screen here to show the demo. All right, here we go. All right, so here I've pulled up my terminal. I've set up a working directory called YOLO v5 OctoML. I've displayed the contents in here. You'll see that first there's a Python virtual environment that I've set up. And there's also a repo in here called YOLO v5. The YOLO v5 folder was actually cloned directly from Ultralytics GitHub repo. So all you need to do is go to GitHub and copy this link from Ultralytics right over here to get the exact same repo. There are three main files in the YOLO v5 repo that are of interest to us. First is the requirements.txt file, This file specifies all the dependencies we will need in our Python environment in order to use the YOLO v5 model. Specifically, there are a set of base requirements here for the model. And there's also 2 extra lines that we will need. One for exporting the model into the serialized Onyx format for deployment, and 2, a dependency on trying client to actually deploy this model. So make sure that you uncomment lines 28 and line 38 before you go and pip install the requirements file. The second file of interest to us is the export.py file. There are comments in here showing how to use this file. The high-level idea is that just run Python export.py and make sure you include Onyx in your export, and that will give you a serialized model file, YOLO v5s.onyx, that you can then use downstream. The third file of interest to us is the detect.py file. So this file basically specifies all the pre and post processing code that we'll need in order to run actual inferences against the model. Note that all of the pre and post processing Python code here is already predefined by Ultralytics. So we can just use this out of the box and not really have to change anything in here. All right, so that's the 3 main files we care about in the YOLO v5 repo. I've already pre-installed all the requirements from the Ultralytics repo into our Python environment before this presentation, just so we don't have to be stuck waiting. In addition, I already ran export.py as pointed out earlier. So you see in the YOLO v5 repo that I now have a YOLO v5s.onyx file in here ready to go. And now that we have all the dependencies and Onyx model file we need from the YOLO v5 repo, let's move on to downloading the OctoML CLI. I've opened up this public link to the OctoML CLI tutorials on GitHub. You can simply scroll down the main README file and you'll find links to the latest version of the CLI binaries. I've pre-installed the one for Mac and moved it to my local working directory to save us time once again. And we can verify that the binary exists in our local path by simply running the command octoml. Now you see all the information we will need, including the version of the CLI binary and what commands we can call to accomplish the task of deploying our model. The first one we should run here is init. What it does is simply help us indicate which model we want to deploy and automatically generate a YAML file to store that information. So let's just go ahead and run it. In this folder, the model I want to deploy is the Onyx version. So I'll go ahead and select that. And now we can display the content of the new deployment workspace file that has been auto-generated for us. We can check that the contents are exactly what we'd expect, right? The model specified in here is YOLO v5s model, and here's the path to the model in our directory. Now we're ready to go and package this model into a deployable container. So I previously already created a container with the same name, so that's why I'm getting prompted on whether I like to replace that. I'll say yes, because I want to create a new Docker container for this model. We'll see that the package has been created, and now we have a container that we can deploy. I'll go ahead and run the next command, which actually gets the container up and running. Right, so the inference container has been started. we have information here about what inputs this container expects, specifically images of the shape 13640, and in the data type FP32. Similarly, we can see what outputs this container will give us. These are tensors of shape 1, 250, 200, 85, and again, in data type FP32. And now we can also run Docker PS to confirm that the container is indeed up and running healthily. We'll see information about the container here. We'll see that it was created 40 seconds ago and has been up since then. And we can see which port we can use to actually interface with this container. So we'll see here it's localhost 8000. That's the entry point to this container. And now we're ready to actually run inferences against a container. Recall that previously we walked over the inference code from Ultralytics repo. It was called detect.py. So now we can simply go ahead and run this detect.py file. We'll need to provide the link to localhost 8000 as a weight into this file, and also provide the path to the image on which we'll run the inference. So I just have a sample image, Einstein original, stored in this repo. I'll go ahead and run our inferences on this image. We'll just wait for a couple seconds here for the inference to run. All right, we're seeing some results. Okay. So we'll see here some information about how long the pre-processing took, how long the model inference itself took, and what was the image that was processed, and where our results are stored. So let's go and take a look at the results. I'll pull up Finder, go to our desired path that the terminal told us to go to, runs detect xp2. All right, so we'll now see the results of the inference. Specifically, there are now bounding boxes drawn on each object that was detected by the model, as well as some confidence scores associated with each detection. As we would expect, the model is able to detect that there's a person, bicycle, potted plant, and so on. And these detections pretty much match what we would expect, meaning that by going through the deployment flow with OctoML containers, the model's correctness was not hurt in any way. This is exactly what we'd expect out of the model. All right, so that's the flow for deploying the model locally. And now let's repeat the same flow for remote hardware to illustrate how we can actually have the hardware independence and be able to move to any remote cloud instance. So what you do is go back to the OctoML command and see what commands are available here. We'll see this add acceleration command that gives you a chance to benefit from OctoML's acceleration technologies to get that hardware independence and cost reduction value prop. So go ahead and run this. This requires you to have access to the OctoML platform at this point. So now you have to upload your model to the platform via this command, and the platform will let you know that it's finished uploading the model to the platform, and now you can select which remote hardware you want to optimize the model for. So I'll just pick one example hardware from AWS, just pick the Skylake one, and then hit return. I'll just pick one hardware target for now, so no, I do not want to add more. And now you see that the OctoML YAML file has been updated, and it indicates which hardware I'd like to optimize for. And now I'll go ahead and create a package again, this time with a flag that shows I want to talk to the service and get acceleration. So now the acceleration has been kicked off. It's going to take a while to complete, so I'll just show you an example of what you can see after the accelerations are done. What I will do is log into the web UI of OctoML right now. I'll go ahead and click onto the project for YOLO v5. You can see here that I've pre-tuned multiple variants of the model. The one of interest to us for the purpose of this demo is the Onyx version. And now we can see a list of packages for each of the hardware targets that I've pre-optimized this model for. I can go ahead and download a Docker tarball for any one of them. I can also visualize how much speed up I got from using OctoML's acceleration technology. Go ahead and click all packages to visualize the speed up. What you see here is the blue dot that represents the best performing optimized version of this model versus all the white dots, which represent the unaccelerated baseline versions. You'll see that for all of these hardware targets, OctoML was able to deliver a speed up over the original baseline. And what that means for you is a reduction in cost per inference. All right, now let's take a look at this Docker tarball that I've just downloaded. And we can inspect the contents inside. You see that there is a build.sh file in here. And basically this bash script just tells you what are all the commands that will get run in the script in order to build a container out of this Docker tarball. So at this point, all you have to do is run bash build.sh with the right flags, and then you'll be able to get a container up and running on your remote hardware. All right, so just to recap, what I've shown you is how to set up your local environment, package and deploy a YOLO v5 model locally, and then deploy on a remote cloud hardware instance while unlocking the hardware independence and cost reduction value props. If you found the demo interesting, feel free to try out the platform for yourself at this link, https://try.octoml.ai YOLO v5. Thank you all for coming today.